Today we're going to turn backwards a little bit. We just finished a one-dimensional rotator, and now I'm actually going to back up, and I want to consider our problem, the particle in the box again. But what I want to do is I want to make it a real box. So we're going to start by thinking about a two-dimensional box. Instead of just a line, x, that a particle is bouncing back and forth on, let's make a box in the xy plane. Let's lay out a square in the xy plane going from 0, the origin, to L sub x and L sub y, and let the particle bounce around inside that square. So we're going to make the potential have an infinitely high wall now at each of those four sides, with here's the energy, here's the potential, and basically the potential is going to be a function of x and y, and it's simple again, it's 0 if x is inside 0 and L sub x, and y is inside 0 and L sub y, and then it immediately goes into infinity everywhere else outside the box. So the question is now, how do we solve this problem? And the basic idea is, first of all, the wave function is going to have to obey the same boundary conditions that we're familiar with. So the infinite potential outside of the box means that the wave function is going to have to go to 0 immediately on the edges of the box, all of the edges, everywhere around that square. And then inside the box, because it's 0 outside of the box, and it again has to be normalized, the probability of finding it somewhere inside that square has to be 1. It's got to curve up away from 0 and come to some finite value inside the square, inside the box where it's confined. So here's what we're going to do. First of all, outside of the box, as we just said, the wave function's got to be 0. So psi, now as a function of x and y, is going to be 0 inside of the box. The potential is 0, and so the Schrodinger equation looks like this, just minus h bar squared over twice the mass times the second derivative of the wave function psi, and now we'll use this Laplacian squared operator to indicate the second derivative in the appropriate coordinate system. That second derivative is going to be equal to the energy times the wave function again, psi. The energy, the total energy, is the eigenvalue of the Hamiltonian, and in the case where the potential is 0 inside the box, the Hamiltonian boils down to the kinetic energy operator, and minus h bar squared over twice the mass times del squared is the kinetic energy operator. So that's our simple Hamiltonian, but now the function's a little more complicated. So first of all, in these Cartesian coordinates, that's minus h bar squared over 2m times the partial squared derivative in x and the partial squared derivative in y. The second derivatives are just completely independent of one another. That's going to be munching on this function psi of xy. And after all of that munching, I have to come up with psi of xy again times some constant, times a number, the eigenvalue, which is going to be our total energy. So this looks kind of daunting. Even just having those two completely independent variables in play makes it a little more complicated. And so what we do is we make this kind of wild conjecture. We just say, I call it a hopeful conjecture. The basic idea is maybe this function of x and y is some function of x times another function of y. And we're going to call that big X of the variable little x is the function in x times big Y is a function of little y, the variable y. And we call this separation of variables. What we're going to go about here is a very general technique called separation of variables. And as you're about to see, it actually works quite well in many, many cases. Now, one of the reasons I'm doing this two-dimensional box this year, where I haven't had time to do it in past years, but it's a good illustration of this principle because it comes out in a fairly straightforward way. So what this means is our function psi of xy, we're going to just hope that it's equal to a function x, which is only varying with x, and a function big Y, which is only varying with y. And so basically, the reason why this is useful is if I take a partial second derivative with respect to x on x of x, y of y, well, y of y is not a function of x, and so it comes rolling right out. It's basically a constant as far as that second derivative, because partial says just look for the x's, ignore the y's, ignore anything else, just look for those x's. So the y of y part of that function just comes sailing right out. So that's the second derivative partial with respect to x of xy, is just y times the second partial derivative of x, the x part of the function with respect to x. So I'm going to call that x double prime y. Likewise, the partial second derivative y is going to be x y double prime. Okay? So we have minus h bar squared over twice the mass times the Laplacian squared. The Laplacian of psi is minus h bar squared over twice the mass of x double prime y plus x y double prime. The separate partial derivatives, second partial derivatives of x and y, and that's equal to the total energy times the wave function, which is now x times y again. And that's a good thing, because now what I'm going to do is I'm going to divide by xy, everything, and I'm also going to multiply by 2m over h bar squared. I'm going to divide by minus 2m over h bar squared. So I'm going to move the minus h bar squared over 2m over to the energy side of the equation, and I'm going to bring that xy function over to the left-hand side. And that just gives us x double prime over x plus y double prime over y is equal to minus 2m times energy over h bar squared. And that's the separation of variables. Because now there's three terms here. One is the second derivative of x with respect to the partial, only the x variable, divided by x. That's the curviness with respect to x. Plus the partial second derivative of the function y divided by y. That's the y curviness of the function. And that's all supposed to be equal to some constant, which is just a minus twice mass energy over h bar squared. But that's all a number, some number. And that's kind of useful. Let's keep working here. We're going to say, in this case, it just happens to be useful. Let's take the energy and split it up. Let's assume there's an energy that I'm going to associate with x and an energy I'm going to associate with y. Energy is a scalar. It adds up. So it's only the total energy we care about. But for bookkeeping purposes, I'm going to associate some with x and some with y. So now I can further separate this equation. I'm going to bring the energy associated with x over to the left-hand side, and I'm going to take the y derivatives over to the right-hand side. And so we get x double prime over x plus 2m e sub x, the x energy, if you will, divided by h bar squared, is equal to minus y double prime over y plus 2m ey over h bar squared. And those two things are equal to each other. And so they have to be equal to some constant value. And here's why. So x double prime over x, that's a function. The curviness with respect to x. X double prime is a function of x. Big X is a function of x. And I can pick any one. Usefully, it's got to be between 0 and L sub x. It's got to be inside the box. But I can pick any single value of x I want. I can pick it. I can hide it. I can write it down. I can put it in an envelope and hide it away. And so this whole term on the left-hand side of the equation, x double prime over x plus 2mex over h bar squared, for some value of x, is going to be some number. But I can pick another value of x and another value of x and another value of x. Meanwhile, over here on the right-hand side, y double prime over y, again, those are functions of y. And I can have any y inside the box, anywhere from 0 to L sub y. So once again, I can pick any value of y totally independently. I write down the x value. Why don't you guys pick a y value? You write down that value, hide it in an envelope like a magic trick. And what this is saying is that when we finish taking that second derivative, adding in the energy, they got to be the same. And the only way that can be true is if for any value of x and any value of y, they're equal to a number. And we call that number lambda, which is why I put it in the middle. It has to be a number. And in this case, 0 is a completely appropriate number. The numbers are these 2m ex over h bar squareds and 2m ey over h bar squareds. Those anything different from 0 is usefully drawn into that number, and the value of lambda doesn't really need to be anything else. So that means that I completely independently now have a function of x It's a differential equation for x, but it's just x. It's a simple differential equation. And a separate equation for y, they have to be equal to the same number. And that's now the complete separation of variables that we were looking for. In this case, curviness is constant is a very, very easy function to solve. We've already solved it for a particle in a one-dimensional box, and it's really no different at all for a particle in a two-dimensional box. So now we're done. We have a function. X of x is equal to sine n pi x over L and x pi x over L. Y of y is equal to sine and y pi over Ly y. There's a lot of subscript y's because that's the associated with the y value and with the x value. And that's when it's inside the box, it's equal to 0 outside the box. The energy associated with x is going to be h bar squared pi squared over 2mLx squared times nx squared for any integer value of nx, 1, 2, 3, 4, 5, 6. So it has to be an integer again, it's quantized. Energy associated with y, h bar squared pi squared over 2mLy squared and y squared. And y is 1, 2, 3, 4, 5, 6, 7, 8, etc. And those only total energy really matters. So the total energy is h bar squared pi squared over twice the mass times nx squared divided by Lx squared plus ny squared divided by Ly squared. For nx equals any positive integer, 1, 2, 3, etc. And ny is equal to any positive integer, 1, 2, 3, etc. Zeros still don't count. I have to get to 0 around the entire square. So I stitch it to 0 all the way around that patch of width, Lx and Ly. And so both the y and the x functions have to be, they have to go to 0 for any values. And so you have to have that curvature in both dimensions for this thing to work. So both quantum numbers go from 1 to infinity, but they vary independently. One of them can be 1, one of them can be 87. There can be 2 at 40. It doesn't matter. They're all possibilities here. A simple case, the energy is h bar squared pi squared over 2mL squared times nx squared plus ny squared if it's square. So if I have a nice square box, then Lx equals Ly equals L. And we have this expression that looks almost exactly like the particle in a one-dimensional box. It's just I've got another quantum number squared that I add in. And it's just totally additive. So instead of just n squared, now I've got two quantum numbers, nx and ny, and I get nx squared plus plus ny squared for the total value of the energy scaled by h bar squared pi squared over 2mL squared. Notice there's some degeneracy here. The energy of nx equals 1 and y equals 2 is exactly the same as the energy of x equals 2 and y is equal to 1. We call that g and it's equal to 2. And this is a way to think about it. If I have the 1, 2 case, then I have a single upward going sign in x and a full cycle of a sine wave in y, and you get this patch that sort of is bulging up as it's toward us and then bulging down as we go away from us. You go the other way around and I get the 2, 1 where it's the full cycle is in the x direction, and now the patch is blumping up and down from left to right as opposed to forward and back. But those look exactly the same if the patch is square. So that I can just rotate it 90 degrees and I get basically the same thing. So it's rotationally symmetrical, so we call that degeneracy g of 2. However, there's other cases, like the 1, 1 case, there's just one state. 1, 1 and nx equals 1 and y equals 1 for that energy. So in this case, there's a distinction between energy levels. So the 1, 2 or 2, 1 each have the same energy level. The total sum of the square of the quantum numbers there is 2 squared is 4, 1 squared is 1, so the total is 5. So the energy at the E12 energy level is 5 times the ground state energy, but there's 2 states as well. So there's 2 separate states with the same energy. It's a degeneracy of 2. The energy level is a value of 5 times the ground state energy. And in the ground state, in this case, there's only one case, and the degeneracy is 1.